consider the following sentence. 1 equals 0. And now consider this other sentence. The topmost sentence on this board is not true. Well, okay, so there's nothing problematic, it seems, with this sentence, right? It's just true. The topmost sentence on this board is not true. So what else? Nothing mysterious, nothing ungrammatical, nothing hidden, no hidden facts, right? Now what happens if I make this, right? Well, it turns out that the topmost sentence on this board is not true, right? Refers now to itself, right? So if this sentence is true, then what it says should hold, and so the sentence is not true. But if the sentence is not true, then what it says holds, so the sentence is true, right? So we get a contradiction. So the sentence is true just in case it is not true. Okay, so this is the famous liar paradox, right? The sentence that says that it's lying. Now, let's take it from a more formal perspective, right? So let's see what ingredients do we need to form the paradox. And some of the key ingredients are, the first place, self-reference. So in order to express the liar sentence, well, of course, we need a truth predicate, right? We need to have a predicate that is true of some items, most likely sentences, right? And we need what it is sometimes called diagonal formation. We need self-reference. So we need names for the sentences of the language, and we need to be able to say that some sentences have this property, some sentences have this other property. Okay, another principle that is at work in a formal version of the liar paradox is what it is called transparency, right? So this is supposed to be a feature of the truth predicate, right? And the general idea, the general philosophical idea, is that saying a sentence or saying that A is true is, roughly speaking, saying the same thing, right? So that you can substitute any sentence by the sentence saying that that sentence is true, right? So that's transparency. The truth predicate is supposed to be transparent in that way. And transparency amounts minimally to the following two inferences, right? Which can be called capture and release. So if snow is white, then you can derive that it is true that snow is white. That seems reasonable. That's called capture because the truth predicate captures the sentence into a name, and you put the truth predicate in front of it. And release, right, because the truth predicate can't release the sentence that it contains. So if it is true that snow is white, then snow is white. Okay, we are not gonna discuss that. There are lots of philosophical literature on why these principles should hold. We are take them on board. You should read some assignment of this, right? But we are gonna hold. We are gonna assume that these principles work. Okay, so let's look to a more formal version of the paradox. So consider the following argument. We've got a liar sentence lambda, which equals its own untruth, right? So lambda equals it is not true lambda. Okay, this is supposed to be a constant, right? This is supposed to be a sentence that is true no matter what happens in the semantics or anywhere else, right? So from the pure truth, so to speak, we've got that either the liar sentence is true or it is not true, right? This disjunction holds in classical logic because it's an instance of what can be called excluded middle. Now suppose that the liar sentence is true. Well, of course, by the inference release, if the liar sentence is true, then we get the liar sentence, and since the liar sentence equals its own untruth, we've got that the liar sentence is not true, so we can put a conjunction with these two sentences and end up with the liar sentence is both true and untrue, right? Now a similar parallel argument can be run from the supposition that the liar sentence is not true, right? Now, I would like you to notice that this, if you take self-reference and you take transparency, you cannot object to these inferences. So there is little room to block the argument, right? And of course, if we can derive one thing from the member of a disjunct and we can derive the same thing from the other member, then we can derive that thing. So the liar sentence is both true and false, right? Sorry, is both true and untrue, right? And this entails, this is a contradiction by the law of explosion of contradictions. This entails anything whatsoever, right? Now you might be thinking, what the hell are you telling me? Now you should have a close look to this video, right?
Are you all right? But there was no explosion.
I lied.
What?
You lied. Everything Harry tells you is a lie. Remember that. Everything Harry tells you is a lie.
Now listen to this carefully, Norman. I am lying.
You say you are lying, but if everything you say is a lie, then you are telling the truth. But you cannot tell the truth because everything you say is a lie. But you lie, you tell the truth, but you cannot, for you lie. Illogical. Illogical. Please explain. You are human. Only humans can explain their behavior. Please explain.
I am not programmed to respond in that area.
In this video, we're going to explain how to extend a language that enjoys self-reference, right, and a truth predicate, and how can we describe some three-valid models for this language in which we can find liar-like paradoxes. Now, I have to say that there is a conceptual jump here, right, because during this course we have been discussing a propositional language in which propositions, simple propositions, are like the bricks, the atoms of our language. But if we want to talk about truth predicates, names of sentences, and all that, we need to make like a further step in the analysis and consider first-order languages. So very roughly, what is a first-order language? Well, a first-order language is a language in which we distinguish between singular terms and predicates. For example, in Socrates is a man, we can take this proposition as a block, right? But we can analyze this sentence and see two different grammatical categories, right? So we've got here singular terms. In particular, here we have a name, Socrates, and we've got a predicate, right? So we will substitute singular terms by these little a's, right? And predicates by p's, right? Now, it is particular of a first-order language that we can generalize over the position of a name, right? So in particular, we can say things like, for every x, x is p, right? And it is called first-order because we can quantify over the position of an individual constant, individual variable, but we cannot quantify over the position of a predicate, right? So that's very roughly a first-order language. Okay, so our language, in order to reproduce the liar sentence, contains a division of non-logical and logical vocabulary, of course. In the non-logical vocabulary, we'll find singular terms, sort of names. We'll find predicates, right? But among the singular terms, there are some special singular terms that are that contain a formula, right, in these sort of brackets. So this is a singular term for the formula A, right? So this name's A, and among the predicates, we've got a very special truth predicate that will behave in the way we want, right? We'll say about this predicate in the semantics. Among the logical vocabulary, we find conjunction, negation, universal quantifier for every x, existential quantifier, there is some x, and the constants both on top, right? This is always false, this is always true. Okay, now let's go for the semantics, which is the complex part of this issue. Not too complex, but a bit more complex than usual. So in the semantics, we need two things, right? We need a non-empty set of objects, right? And a function mapping each expression to an appropriate entity, right? According to the grammatical category of that expression, right? So in particular, singular terms will be interpreted with objects in that domain, and predicates with subsets, sort of subsets of objects in that domain, right? More particularly, since we've got a language in which we've got singular terms for the formulas of the language, the domain should contain all the formulas of the language, right? That's reasonable because the formulas of the language are going to be the reference of these names. And the interpretation function will behave in this way. For each singular term or individual variable, the interpretation will give an object into the domain, right? So the idea is that D is a set of objects, right? So our interpretation function will interpret singular terms with objects in that domain. In particular, for each name of this form, the interpretation function will give us the corresponding sentence, right? That's no surprising thing. Now, for each predicate, the function will give us a function from the domain to the three truth values, right? This might look a bit more abstract, but the idea is simple, right? Since we want to make use of three truth values, instead of interpreting predicates with subsets of D, we interpret predicates with functions going from objects in D to the three truth values, right? So that when we apply a function to a singular term, this sentence will render a truth value either 0, half, or 1, right? Okay, so that in particular we can very easily say that the interpretation of a sentence of the form PA, where A is a variable or singular term, is the result of applying the function with which P is interpreted to the object with which A is interpreted. Now, in the particular case where we've got sentences of this form, it is true that, and we've got the name of a sentence, the value of this sentence should be the same as the value of this sentence, right? This will guarantee transparency. Right? The idea is that it is true that A in any model has always the same truth value as the sentence A, right? As the truth value of the sentence A in that model. And all the rest is completely standard. So conjunction takes the minimum. Negation maps 1 onto 0, 0 onto 1, and the middle value onto itself. And perhaps the new thing, which is the universal quantifier, well, this is a generalization of conjunction, right? So what does it mean that every object satisfies a condition? Well, that this object satisfies the condition, and this object satisfies the condition, and this object satisfies the condition, and so on for every object, right? So the truth value of an universally quantified statement is the minimum of all the instances, right? So the minimum of all the sentences in which we, so to speak, consider X variants, right? So we move the interpretation of the variable, the bounded variable by this quantifier, consider this instance and get the minimum truth value, right? So that's just the idea for that. Okay, so this is the semantics for a language enjoying a truth predicate and names for the sentences so that we can have self-referential sentences. Now, as in the previous case, we've got the question of how to interpret the middle value, right? So should the middle value be a way of being true? Should the middle value be a way of being untrue, right? Well, that depends on your definition of truth in terms of strict or tolerant truth, right? If truth is interpreted with having value 1 is truth, if truth is a strict truth, right? Then the corresponding definition of logical consequence will be K3, right? But it will be a K3 definition of logical consequence over a semantics, first order semantics with self-referential sentences and all that. If we take tolerant truth, right, and define logical consequence accordingly, we can call this, not to confuse it with the logical consequence not having to do with a transparent truth predicate, we can call it K3 plus and LP plus, right? So this is a version of the LP logic for a language containing a truth predicate, liar sentences, and all that, right? Just a small remark, right? So there is a construction called the Kripke Construction, which shows how to construct models, right, in which the truth predicate behaves in a transparent way, right, and in which not just this liar sentence, but any paradoxical sentence gets always the middle value, right? And this is precisely, if you want to go this way, this is precisely the sort of thing you want to have, right? Why? Well, because the liar sentence and its negation, if truth behaves in a transparent way, the liar sentence and its negation should have the same truth value. And this happens only if the liar sentence have the middle value, right? So in the next video, we are going to explain how to deal with tableaux for all these very fancy things. Now, for the sake of completeness, we are going to explain how the rules for quantifiers and the new constants for this language work. Okay, so you know everything you need to know roughly about tableaux. There are lots of interesting things that have to do with tableaux. In the case of quantified first order logic, there are some rules you should know, right? So everything works roughly the same as in classical logic, right? And about the tags, right? About the tags, whether we are dealing with strict or tolerant satisfaction, we proceed in much the same way as we did with the propositional case, right? So carry the tag alone, and the branch will close if you have something different. You have A and not A, but not both tolerated, right? One of them should be, at least one of them should be strict. Okay, so the easy rules of the quantifiers are these two rules. The rules tell you that if you've got negation of an existential quantifier, you can move the negation in and change the existential quantifier by a universal quantifier. Intuitively, it is not the case, so it is not the case that exists an x that blah 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 is the same that for all x it is not the case that blah blah blah, right? So you can, this like funny thing, you can move this in and change the quantifier, right? And for the other case, it's much the same thing, right? So not for all x, blah, 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 is the same as there is an x such that it is not the case that blah, blah, blah. Right? So move this in, change the quantifier. That's easy. And you carry the tag alongs. If you are making the tree for strict, you carry the tag along and put strict. If you are doing it for tolerant, then you carry the t, right? Now these other rules might be trickier, and in fact it might be more difficult to see the rationale behind the rules, right? Actually, completeness for a propositional tableau-based proof theory is something relatively trivial. In that case, you should show that the thing works, and I mean, giving a full justification of the rules is providing a completeness result, right? I'm going to give you just the intuition. Okay, so as always, you carry the tag, right? Suppose that you've got that there is an x such that x fulfills some condition A, right? Now you should eliminate the quantifier and substitute the bounded variable by a new constant, right? Why? Well, because you know that there is an x that satisfies the condition, but you don't know which x is it, right? So if you substitute this x, this variable, by something that is already in the tableau, you are substituting this variable by something that is somehow new, right? That you have some commitments on it, right? So it is important, in order to cover the most general case, right? It is important that this constant should be new, right? Actually, this is a sort of reasoning, a very general reasoning in mathematics. When you prove something about an object on which you don't have any commitment whatsoever, then you have given a general case, right? A general proof. And this is something also very peculiar of first-order logic. If you've got the universal quantifier, you should, so the rule tells you to eliminate the quantifier and substitute the bounded variable by every name or every singular term on the tableau, right? And it might look that you should substitute, because some objects might not have a name, right? In the model, when you look at the semantics, you can have a model in which some objects are not named by any constant, but actually it can be proved that it is enough to cover all the cases if you substitute the bounded variable for every singular term on the tableau, right? Actually, on the branch. Okay, so the other rules are quite easy. If you've got the verum, right, the constant that is always true, you've got it negated, well, you change it by the constant that is always false, reasonable. If you've got the constant that is always false negated, then you change it by this, right? If you've got this constant and you are checking for either strict or tolerant satisfaction, then you should do nothing, right? Because this is satisfied in any model whatsoever. If you've got this constant, the falsum, checking for strict or tolerant satisfaction, then you should close the branch, right? Because this is false, this is neither strict nor tolerantly satisfied in any model whatsoever, right? This closes the branch automatically. Now, I'm not going to tell you the rules for the liar, right? So I tell you that you should consider these two cases: the liar when you are checking the liar for strict satisfaction, and when you are checking the liar for tolerant satisfaction, right? You should try to figure out what the rules for these cases are, right? Cool, very good, we are done. We have explained K3, OP, how can you combine these logics with a transparent truth predicate and self-reference, and now it's turn to go to the question of the liar paradox and the argument, and how these logics can help us in solving the argument, right? Okay, so this is the liar argument we presented at the beginning, and as we commented, these inferences, so basically the structure of this argument is like an argument by cases, right? So from each disjunct we make an argument to these contradictions, right? So we can end up with a contradiction, right? And as we said, these inferences are all based on self-reference and transparency. Right? This means that these inferences are not to be questioned under the present approach to truth, right? So it seems that the only thing that are left are the inference from the truth to this statement and from the contradiction to the falsum, right? And actually, these are the inferences that are going to be questioned by K3 on the one hand and LP on the other, right? So recall, K3 is a paracomplete logic, right? In the previous case was empty on the left, right? So there are no valid sentences. No, we have some valid sentences in this case, but in the most basic language, there are no valid sentences. And in particular, people holding K3 are going to argue that this first step, this first inference, what it is sometimes called the law of excluded middle, is to be questioned, and in particular is to be questioned in the case of the liar, right? Recall that the liar sentence in Kripke's fixed point models, the liar sentence gets always value half, right? So this whole sentence, when A is substituted by the liar, takes value half, and this means that it's not K3 valid, right? What's the move with LP? Well, the move with LP is the dual move, so to speak, right? I would like you to notice that this inference here and this inference here are each other's dual, right? So we move this to the other place and put a negation. We move this to the other place and put a negation, right? So these inferences are perfectly dual, right? And this is the principle of explosion of contradictions that we know that fails in LP, right? And in particular, it fails when A takes the middle value, as it is the case of the liar, right? So far, so good. The weakening of the logic, in a sense, is helpful if you want to hold a transparent truth predicate and self-reference, right? But I would like you to notice that there is some collateral damage, right? So in particular, there are some inferences related to the material conditional in either LP or K3 that make this conditional very unappealing for lots of purposes, right? But in particular, in LP, we know that modus ponens in inference form fails, right? So this is a very fragile conditional. In K3, perhaps more dramatically, in K3, this is not valid, right? Because K3 has not validities on the left, right? And this means that in particular in K3, the principle, so in K3 we've got a transparent truth predicate, right? But the principle, suppose that this is a material biconditional. So the principle expressing in the language that the truth predicate is transparent is not valid, right? So in a sense, it's like a limitative result when you want to express some facts on the object language, right? That's truly a pity of K3. Okay, even further, right? So when you lose, so the general strategy of these logics, of this approach to the paradox of the liar, also to the Sorites, is, okay, so we've got problems with classical logic, so let's weaken the logic, right? Let's reject some inferences, right? Okay, yeah, but rejection of inferences always come at the price of rejection of some meta-inferences, right? And some of these particular meta-inferences, by meta-inference, I mean relations between inferences, right? So no particular inferences, but the way some inferences relate to another. So some of these, so for example, one particular case of the failure of a meta-inference in both K3 and LP is what it is called the deduction theorem, right? It is supposed to be a meta-inference related to our intuitive understanding of the conditional, right? So that's the point, right? In the next video, we are going to introduce a solution that is somehow connected to both K3 and LP, but I would say that fares much better than these solutions. Very well. This is the last video, so I prepared something special for you, right? I'm going to present a very new solution to the liar paradox, in which you can have a transparent truth predicate, you can have self-reference, and you can have classical logic. Some people think that this is just impossible, right? But these guys, David Ripley, Paul Egré, Robert van Rooij, and I myself, we have developed such an account. Okay, I'm going to try to sketch how the things work, because this account is very much related to what we explained already about LP and K3. So just to remind you, so in the case of K3, we've got here the liar argument, right? In the case of K3, this inference, the excluded middle inference fails, right? And this is what blocks the argument. In the case of LP, is the dual inference, the explosion of contradiction, what fails, and this blocks the argument, right? And instead of giving a definition of logical consequence that makes like or privileges one notion of truth, we define logical consequence in our ST style, right? So delta is an ST consequence of gamma, just in case there is no interpretation where all the premises are strict and no conclusion is tolerated, right? So this ST logic permits valid inferences from strict truth to tolerated conclusions, right? Okay, so it turns out that based on the same Kripke models, right? This is a picture that gives you the information about the extensions and conservative extension between these logics, right? So we've got here at the bottom the logic going from the tolerant premises to strict conclusions. In the simple case without the constant stop and both the verum and falsum, with the exception of that constants, that logic is empty, right? Now we've got LP, which is preservation of tolerant truth. This is for the basic language. We've got K3, which is preservation of strict truth. And we've got classical logic, which in a three-value setting can be defined via ST, right? Now, when we add a truth predicate, when we add self-reference, and when we are quantifying our logic quantifiers over Kripke models, we get these conservative extensions, right? So this is LP with a transparent truth predicate over Kripke models, right? It's a conservative extension in the sense that anything that is valid here in the old vocabulary is valid here, right? Sorry, anything that is valid here for the old vocabulary. Now this is a conservative extension of K3, right? So enjoys a transparent truth predicate, self-reference and all that, but the excluded middle inference fails. Now the striking feature, right, the really amazing thing is that you can have a conservative extension of classical logic. So ST plus, right, in the same way you can define from LP this logic with a transparent truth predicate, and in the same way you can define from K3 this logic with a transparent truth predicate. You can start from classical logic and define this logic with a transparent truth predicate, right? So going back to the, very quickly. So what are the benefits? Some of the benefits of this, that you don't lose any inference, right? Not even in the expanded language. So for example, in the case of K3, we have that this is not valid, not at least if this is the material by conditional, right? And we lose some meta inferences as well. But in the case of ST, or better, ST plus, this is perfectly valid, right? So you can express in your own object language that the truth predicate behaves in a transparent way. Now let's go back to the argument, right? So we've got that this inference is not K3 valid, but since ST is a conservative extension of classical logic, this inference is okay, right? So excluded middle holds. All these inferences are granted by self-reference and transparency, and this last inference also holds, right? No, but we know that ST is a conservative, ST plus is a conservative extension of classical logic, so we cannot have that this argument, the whole argument is valid, right? So we cannot have this. We cannot have that from the truth we infer the falsum, right? So what's wrong here? Well, as it happened in the case of the Sorites, our ST plus logic is non-transitive, right? And in particular, so this inference is ST plus valid, right? Why? Because the liar sentence has value half in every Kripke model, right? And this prevents the finding a counterexample to this inference, because in order to produce a counterexample to this inference, the conclusion should have value 0, right? And lambda has always value half. Now this inference is also valid, right? Because in order to produce a counterexample, premises must have value 1, right? And the liar sentence always get value half in Kripke models. But of course, this inference is not valid, right? You might think, well, it is too much losing transitivity. Well, I don't think. I think all these benefits are worth any other cost. And it's been a pleasure. And I hope you enjoy these videos and the course and everything.